Now I want to spend some time talking about the most fundamental sort of problem in all of group theory, and in fact, all of abstract algebra. And this is why the notion of isomorphism is so important. Remember that isomorphism tells you what actually matters. It cuts out the fat that doesn't matter, like are my elements called E, A, B, C, or are they called something else, right? Y, 6, B, coffee cup. It doesn't matter, right? If they have the same group structure, that's all you care about. And so the most fundamental sort of problem in all of group theory is a sort of classification problem. And what I've done here in the box is I've sort of given language for the most basic sort of phrasing of a type of classification problem. So here's what a basic classification problem will look like. Determine a complete list of groups of type T up to isomorphism. Okay, whatever type T means, who cares? It's some sort of property that you care about. So type T is just some condition you care about. And I want to explain what it means when you see these verbs. Determine this list, right? And then this phrase here, what does it mean to do it up to isomorphism? This is a phrase that you see all the time in mathematics. Up to isomorphism. What does that mean? So here are some examples of such classification questions. You might be charged with finding all non-abelian groups of order 14, right? Find all of them. That might be a classification problem you're given, right? And again, up to isomorphism is always there, even though we don't say it, okay? You might be charged with finding all abelian groups of order 30, let's say, okay? You could be charged with that question. You could be charged with finding all groups, whether or not they're abelian. Who cares? Find all groups of order 510. I'm just making up numbers here. You might be charged with finding all cyclic groups, right? And these are examples of the basic classification problem. Find all cyclic groups up to isomorphism. So the type would be cyclic groups. Here, the type would be non-abelian order 14. Here, the type would be abelian order 30. Here, the type would be 510. Order 510 is the size of your group, right? And so we want to solve such questions up to isomorphism, okay? But what does that mean to solve such a classification problem? What I'm going to do is just look at an example, and we're going to try to do these together as for the rest of the semester, because such problems are really interesting, typically because they are very, very hard. And solving classification problems is really, really fun in mathematics and group theory. So here's a classification problem. Let's suppose I charge you with finding all abelian groups of order 8. All abelian groups of order 8 up to isomorphism. This means that you must do 3 things, okay? And typically, none of these 3 things are easy. We're going to learn some techniques the rest of the semester that will make parts of this procedure, this approach, easier, okay? But typically, none of them are easy. Classification problems in group theory are still open. There are still unsolved classification problems in group theory, okay? We're going to solve some together this semester. So suppose I charge you with finding all the abelian groups of order 8 up to ISO. Here's what you got to do. First thing you got to do is you must actually provide a list of groups of order 8. And you got to show that they're all abelian. So this shows that you have a list of potential candidates. I wanted you to find all the abelian groups of order 8. One thing you should do if you're going to give me an answer is to make sure that your answer contains groups that are order 8 and that are also abelian. This is called candidacy. Is your list an actual list of acceptable candidates? Are they abelian of order 8? You got to do that. That's not too hard. You can check that things have 8 objects in them. You can check that a group is abelian. You can do that. Now it gets a little bit harder. You also need to prove that there are no redundancies in your list up to isomorphism, right? So you need to show that no 2 groups in your list are isomorphic. You don't want to give a list that has written down the same group twice, where now when I say the same group, I mean isomorphic. You don't want to write down the 2 isomorphic groups, because then you're redundant. So you got to make sure that no 2 groups in your list are isomorphic to each other. So there's no redundancies up to isomorphism. And here's the hardest step typically. You then got to prove that your list grabbed all of the options. You got to prove that any abelian group of order 8 in the whole universe is isomorphic to one in your list. That means your list is complete. That's called completeness. So you now got to take a general, random, abstract, abelian group of order 8 and then prove that group is isomorphic to one of the groups on your magic list, and that's called completeness. Once you've done that, then you have successfully classified all abelian groups of order 8. Okay? Now this problem is actually solvable, right? And the answer is that the classification consists of 3 groups: Z8, Z2 cross Z4, and Z2 cross Z2 cross Z2. In other words, all of these are groups of order 8, and they're all abelian. That's true. No 2 of them are isomorphic to each other. We'll get into that later. It's not too hard to prove. The harder thing to prove is if I take any random abelian group of order 8, it must be isomorphic to one and only one of these groups. So these 3 groups here provide a complete classification of abelian groups of order 8. Thus, we can summarize this by saying there are 3 abelian groups of order 8 up to isomorphism. The groups in this list are then called the models. Okay, so these are the 3 models of the isomorphism types of abelian groups of order 8. Okay, if you want to see how this stuff can get difficult, try the same thing, but change the classification question to finding all the groups of order 8. Get rid of the abelian adjective. Try to classify all groups of order 8. Well, you found the abelian ones here if you believe me, but what about the non-abelian ones? Do you know the non-abelian groups of order 8, and can you find them all? That's a much harder problem, okay? This stuff is fascinating, and we're going to work on that over the next few lectures, and we're going to find some techniques to help us solve such classification problems.